And we have one more objective to look at the infinite sum, where you just keep on going, keep on going. So this is called an infinite geometric series. And we write this summation notation. We say let k go from 1 and then keep on going to infinity. And we have a sub 1 r to the k minus 1. Well, in real life, in calculus, you're going to say, let me do the limit as n goes to infinity of k equals 1 to n. And you're actually going to look at this as a limit. But we're not going to worry about that yet, but I just want you to realize that you can't actually add up an infinite number of terms, but you can find out what they would add up to by the limit ideas that you learn in calculus. So recall that we call the sum of the first n terms the nth partial sum. So S sub 5 is the fifth partial sum. Add up the first 5 terms. So we had a formula from the previous movie where we said, well, S sub 1 is a the first term times this ratio of 1 minus r to the n over 1 minus r. Well, can you see that if I distribute the a to each part of that fraction, that I'll get a1 over 1 minus r minus a1r to the n over 1 minus r. So that gives us this formula. And as n gets really large, if that starts approaching some number like 3.2 or 1, then we say that this infinite geometric series converges to that number L, in fact. So we call L the sum of the infinite geometric series, and we write that they are actually equal. If a series doesn't converge, it's called a divergent series. So convergence of an infinite geometric series says this only happens if the absolute value of your r is less than 1. So remember, we learned earlier that that is the same thing as saying that r has to be between -1 and 1. So remember solving absolute value inequalities, this is another place where they are useful. So if your r is between -1 and 1, then it turns out that the infinite geometric series converges. That's the condition that you have to meet to get convergence. And its sum, it actually adds up to a number, which I find totally amazing. Its sum is a sub 1 over 1 minus r. Because what happens is this term gets smaller and smaller and smaller, because think about if r is a half. When you keep multiplying a half by itself over and over and over and over, it's getting tinier and tinier and tinier. So this part is actually going to 0, and so that's why all you have left is that first term. So this is on your pink sheet, and that's the sheet that will be provided on the final exam. So you don't need to memorize this formula. You need to understand it and be able to use it. Okay, so here's some examples. We have to decide whether the series converges or diverges. So you just look at how big is r. So this one, you say 2 divided by 6. So it looks like we're multiplying by 1/3. 2/3 divided by 2. Well, that's 2/3 times a half. So that's 1/3. So r equals 1/3. So the series converges. And it says if it converges, find its sum. So the sum from 1 to infinity of 6 times our r is 1/3 to the k minus 1 adds up to 6 over 1 minus 1/3. So that's 6 over 2/3. Or 9. It adds up to 9. So as you keep adding more and more terms, that number gets closer and closer to 9. And in fact, the limit is the number 9. So let's look at the rest of them in class together. because I want to get to this. I find it really interesting, repeating decimals. So if I have the number 2.351515151 and it keeps going, remember that we write it like this with a bar over the 51. So I'm going to write this as the number 2.3 plus 0.0515151, and there's a reason for this. I'll tell you in a minute. So I want to just keep this part over here separate because it's not a repeating part. So it's not of interest to me at this moment. So now I want to write this repeating part as 0.051 plus 0.00051 plus 0.00051 plus, and so on. So take a moment and see if that makes sense to you, that if I add these together, I start getting that repeating pattern of the 51515151. And to get from one term to the next, if I do 0.00051 over 0.051, remember that you move the decimal place over. So I'd have 0.51 over 51. And move the decimal place over, which is 51 over 5100, which must be 1 over 100. So R is 1/100th. That's definitely smaller than 1. So this geometric series converges. And in fact, what it converges to is A, the first term, over 1 minus R, which is 1 over 100. So it's 0.051 over 0.99. So we can find that number with our calculator. Let's see, 0.051 divided by 0.99. And indeed, that is the repeating decimal number that we're trying to represent. So we're going to multiply by 10, 100, 1,000 on the top, 10, 100, 1,000 on the bottom, and get 51 over 990 exactly. So now I go to this first part, the 2.3, to add that. So I'm going to have 2.3 plus 51 over 990. Well, 2.3 can be written as 23/10ths, right? Think about it for a minute. 2.3 is 23/10ths plus 51 over 990. Well, that means if I multiply this fraction by 99 over 99, I will get a common denominator. So I'm going to do 99 times 23. So that's 2277 990ths plus 51 990ths. So that looks like 2328 990ths, but clearly those numbers are both even. So we should try and reduce. So I'm going to get 1164 over half of 990 is 495. And I don't think I'm going to reduce anymore because this one's a multiple of 5 and the one on the top is even. So you can ask your calculator if you can keep going. And maybe you can. There's a 3 in here and a 3 in here. So let's do 1164 divided by 3. So that's going to give me 388. Your calculator will probably do this faster. 495 divided by 3 is 165. Now I think we're reduced as much as we get. So to me, it's fascinating that you can write this repeating decimal as 2.351 bar as exactly this fraction. And so you could try on your calculator doing 388 over 165 and see if that's what you get. Pretty amazing. So that's it. There are word problems that go with geometric sequences, but we're just kind of out of time. So we're going to call it a class. It's been great.